Welcome everyone. Okay, so symplectic geometry continuation. So we remember what were the last notions that we had. So we started with a symplectic manifold, and we were looking at coisotropic submanifold. And we showed, okay, the definition was that the tangent space to C, take its orthogonal complement with respect to the symplectic form, it lies in itself. And we showed that this is actually equivalent to the fact that the vanishing ideal is a Poisson subalgebra. Vanishing ideal of C. And then we showed that you can do coisotropic reduction. So you can do. So we define distribution D to be kernel. So we pull back symplectic form to the submanifold. You get something that in general is degenerate. But this thing was actually a involutive distribution, or integrable distribution. And we define the reduced space to be simply the coisotrop model by null leaves of this distribution, the integrable leaves of this distribution. And we showed that algebraically, if everything goes well, this you can describe as a Poisson normalizer model by the ideal itself. Okay, so and then we discussed. So this was the and then we define Hamiltonian T-space. So coisotropics, and then we define Hamiltonian T-space, which was a datum of a symplectic manifold, which is being acted upon by a group. And actually here, let me address something. Okay. Being acted upon a group, by a group, and there is a map to the dual of the Lie algebra, and it satisfies two conditions. One of them was that mu is G equivariant. Here we assume that the group G was connected. That was our only assumption. And second, we wanted that the fundamental vector fields are all encoded in terms of the moment map, which is what this map is called. And here, just to address something that the point that was raised by Frederick the other week, and I had the sign wrong there. Like the way to define the fundamental vector field using the V action. So this is the left action. Is that you need to put the minus here. So I think at a point M.
By which you mean the left? Oh, it is the left multiplication.
Yes.
That makes sense.
Okay. And then we show in particular this shows that omega itself is preserved by the group. We gave some examples of coadjoint orbits, namely the sphere was our main example, and then you can have, if each time you have a Lie group, on its dual you have the coadjoint orbit, so they are naturally symplectic, they are naturally Hamiltonian even with respect to the original group, but if you take any subalgebra or any subgroup of the original group, then Hamiltonian descends to that, so in this way you can get like sphere acted upon by one-dimensional rotations. This comes from this. But, we have this thing acting on two spheres, which are the coadjoint orbits, and restricting it to SU2, you get like usual setup with a sphere being rotated like this. Because making a subalgebra here means that you can post-compose this with the projection on the page. Okay, so that's a bit, and then we mentioned some very interesting statements which we didn't pursue further. Just I wanted to mention like the polytopes. And now let's go back to the stuff that we're interested in. So, okay, let me formulate this proposition. So, one of the basic things that you want to do, that people do with such Hamiltonian G spaces, is that you can reduce them, and indeed you will see that you can reduce this in a sense to coisotropic reduction. So I will do it in 2 steps. So let me first start like this. So let's M be a Hamiltonian G space. And I will assume that such that 0, which is inside the target of this moment map, is a regular value. Okay, I will comment what that means at the end.
That is O or 0?
That's 0. O I try to do like more perfectly. Slightly more perfectly. 0. So 0 is regular. What does it? Let's say what regular value means. Regular value means that for all points in M which are in the preimage of this, so it's 0. But for all such points, the push forward map is surjective. Okay, this thing, which is something that goes from here to the tangent space at 0 of G star is surjective. Okay, so it's a technical condition that you don't really need to worry about. Okay. So then the submanifold.
So sorry, it's a technical condition that maybe one can say that is never satisfied for quadrant objects.
Yeah.
Yeah. So
True. Yes.
actually, I should still check it.
It's for a zero-dimensional group.
Yes. Yes.
Yeah. So we will see we will soon see the more general version where you can. We will soon see the more general version, the version where you can put anything in here. Exclusive, anything that's regular value. But yeah, okay, fair point. Not satisfied for quite a lot. Okay, so anyway, so then we kind of this preimage is actually co-isotropic. And we can also say very nicely what D is. And with the integral leaves of D being G orbits. Orbits of G. Probably sounds better. Okay, so this thing fits in our previous context. And let's prove this. Okay, so let me call this. And then consequently we will see that you can make a reduction if you move this out, but I will say that at the end. So far let's just prove this thing. So let me call this would be submanifold C. Okay, and let's take a point in there. And let's calculate, okay, so there is 2 observations. So one observation is, okay, maybe picture would be good at this point. So this is our manifold M, and this is our moment map which goes into G star. G star is some linear space. So let me draw it like this. Now the preimage of 0 will be some submanifold. Again, for lack of dimensions, let's imagine that it's some sort of surface in here. That's the preimage of 0. And well, we know that the moment map is G equivariant. And 0, and what is the action of G? Both sides have an action of G, right? And we want that this moment map interpoints these actions. Now, the action here was the coadjoint action, which is a linear action. So, in particular, 0 is preserved by G. So, the stabilizer of 0 here is the entire group G. Which means that if I sit in a point in here, and such that I map to 0, and I act with it on G, I should still be mapped to 0. Yes.
Because the map is G accurate.
Because the map is equal, yes. So first observation is that the orbits are actually, like, if I take my point here and I take the, okay, let's call it, this is O, so this is the orbit passing through O, and that thing is contained within this thing. So in particular, the tangent space with that orbit is contained within the tangent space of C. See this.
Yeah, but what is the O?
O is the orbit. Oh, this is the orbit passing through M. G orbit of M. All the points where I can get by acting with G. And by this argument, they should still get mapped to the same point. So they are inside that orbit, and hence the tangent space is also inside the tangent space to this submanifold. Okay. Any confusion? Everyone happy? Who is unhappy?
And then the point of the regular values that I will tell you.
Okay. Yeah?
So I think M is three-dimensional on the picture.
Yes?
And you have into a three-dimensional space and the pre-image of 0 is two-dimensional, then you cannot expect the map to be perfect. But it's very stupid, it's a very stupid point. Because you have two directions in M keep you in 0, so the third dimension lets you go somewhere in.
But this picture is misleading. This is symplectic, so it needs to be even dimensional anyway. So.
Okay, sorry. I didn't want to go that.
Okay. So there is nothing wrong in the ideologically.
Yeah.
It's just in the drawing.
Yeah, it's 4 dimensional.
Yeah. This is clear from the picture. Okay, good. So now so now let's calculate what the tangent space to C actually is. Maybe we have a good handle on what this thing is. Okay, so what is this? So how is C defined? It's the pre-image of this. So what is the tangent space? It's the it's all the vectors that don't throw me out of like it's the vectors that don't change the value of mu. So they still land at the same value. So this is all the, if you want, this is the kernel of the push program. So it's all elements in here. Well, such that if I take my vectors here and I differentiate this mu, so mu is really a function on M rather than some vector space, and I want this to be 0. Here I regard mu as a function on M valued in a vector space. So the tangent space, what is a tangent space? A collection of vectors that are tangent to my space. How do I stay tangent? I stay tangent if I don't change the value of mu because I want to be a primitive 0. I don't want to go out of it. Okay, so now let's just rewrite this. What does this really mean? This condition? Well, first of all, this is the same. Okay, I want to get to this one. This is where I'm heading.
Wait, how do I see the mu as this tensor? I thought that it was a manifold.
Yes, it is.
But the manifold is M, not C.
Yeah, but mu is a map of manifold.
Oh yeah, I get it. Yes. All right, yeah. I just tensor it up. Yep.
Yeah. So okay, so what I can. This is the same as saying this. But mu is not valid in a vector space, so this is the same as saying that. Okay, I just rewrote the same condition. Right, the mu was only one function, it was a bunch of functions, they were valid in a linear space. So saying that something is 0, this is still valid in a vector space. So I can just as well say that I pair it with any vector in G. Okay, I wrote it in this form so that I can use the condition that I have over there. So continue. So okay, so this means that so yeah, so this is all the collection of all vectors here, such that for all x in G, I have I of v, and then this I of v d of mu x 0, and here I use now our Hamiltonian condition. So this thing says this. Okay, so overall, what this thing says is that omega of v and xm is supposed to be 0. But what is xm? Xm is the fundamental vector field generating my g action. So if I say that I have a vector that is orthogonal to all the fundamental vector fields, it means that I have something that's orthogonal to the orbit. So this is the same as to say that these are v such that v is orthogonal to the tangent space of the orbit. Orbit, sorry. We're orthogonalizing here, this is with respect to omega. Okay, so well, this is simply the orthogonal complement of this thing. And that's it. Because now I know that, in particular, I know that this thing, sorry, right, what do I know? Yeah, because in particular, to check coisotropy, I need to check what this is. And by that, you see that it's the tangent space of the orbit, which is contained within itself. Okay. So the proof had two parts. First, an easy realization that the orbits are actually inside there, inside C. And the second part, which showing that the tangents, the orthogonal complement of the orbit is actually precisely the whole C, tangent space to C. Okay. And also we see that D, which was the kernel of omega C, that's the same thing as this. We see that that's precisely the orbits. So the D is also, we see that D is the tangent space to the orbits. D at point M is the tangent space of the orbit. And hence, if I integrate it, I get the orbits. That's what the thing says. Okay, any questions? Okay, so in particular, we see let's call it corollary. Corollary. Corollary of this is that if the action of G on this pre-image is free, then this thing is symplectic. Because it fits into our picture of coisotropic reduction. I take a space which is coisotropic, which is my pre-image of 0, and I mode out by 0 leaves of omega, which is precisely the orbits. So this is the space I get. And yeah, so these technical conditions that we had two technical conditions. There's a condition of regularity which is simply there to say that this the role of this condition is to say that this subspace that I have is actually a submanifold. That's the role of this, if you want. And then I want this in order for the quotient to be nice or something. But yeah, we don't, that's not really the important part. Okay, so now we see that the Hamiltonian space is also linked to some interesting reductions, at least when 0 is a regular value. So now let's do the more general version. So this I will call theorem. This is called Hamiltonian reduction, or Hamiltonian, or Marsden-Weinstein. Reduction. I think some people also call it simply symplectic reduction, right? Okay, maybe not. That's not. Okay. So this is the general value. This is the general form of the theorem. So let M be a Hamiltonian G space. And now let's take an arbitrary element psi in here. We want this to be a regular value. Mu. And the condition is that now I want G psi, which I define this to be the stabilizer of the point psi in G, the subgroup that preserves this point. So I want that this thing acts freely, again, it's a technical condition, on the preimage of psi. Then the claim is that I can define a space, and this is often denoted by this double quotient. Now, some people try to keep track of the fact that we use also psi in this, and I forgot maybe the question for experts, like where do I put the psi? Do people put it here or here?
I put it on the bottom.
At the bottom, okay. Here or here? Here.
Yeah.
Where?
Yeah, I do that.
Okay, so this thing is defined to be the preimage of this thing modded out by the stabilizer. That's the more general version. In the case where the psi was 0, then we saw that the stabilizer of 0 was everything, so we get this in particular recovered the previous statement. But there's also a different way to state this. We can say that this is easy to see, that this is the same as taking the preimage of the entire coadjoint orbit passing through psi, and then modding this out by G. Sorry, this is symplectic. And not just that, but I mean, really, the symplectic form is the one naturally constructed from it, but I wrote the formula like this because you will see from the proof how this relates to the question of the reduction function. Or maybe I should say it. Should I say it? Well, let me keep it like that.
Let me say that, I'm sorry, but again, for quadrant objects, again, these are not, it will never be a regular value. Almost. Can quadrant orbit, because according to for the inclusion of the quadrant orbit,
yeah, but also,
yeah, if you do it, I think the quadrant orbit will need to be like an open subset of the real of the zero.
Yeah.
I don't think this can happen.
No, this happens often.
This happens?
Yeah. Like if you take like two-dimensional, non-abelian algebra.
It's a point.
Orbits are open, but still, yeah, okay. So even though the quadrant orbits themselves might not be good examples, but it's really like you can always find a subalgebra, and like it should probably work if you just restrict the subalgebra potentially. No? It could.
I think my point is that this theorem holds also for more general assumptions than just a regular value. I think it's a convenient assumption, but it's not
I see.
restricted. Because I guess what it uses some kind of constant rank theorem to say that the tree which is if the differential of the map is surjective, then it has constant rank, but there should be also like weaker
Right.
situations. Thanks.
Okay, thank you. Thanks for the, yeah, good. So now let's do this. And the trick is to reduce it to the previous proposition. So we know that this thing works if we would be looking at a pre-image of 0. So let us modify the problem such that this is a pre-image of 0. Well, one thing you can do is that you can, one thing that you might think you can do is that you can say that, okay, I just shift my moment map by a constant psi, but that won't be a moment map anymore because the G variance, the G equivalence condition will require that this element is invariant. So that doesn't work. But you can do something else. So let's define a new symplectic manifold as the product of the original manifold and the coadjoint orbit of psi. And this bar here means that I take opposite omega. I take minus symplectic form. That's the standard notation. So by this I mean that as manifold it's a product, but the symplectic form is not a sum, but it's like symplectic form here minus symplectic form here. And now we know that both of these spaces are Hamiltonian. First one because we are assuming that, and the second one because it's a coadjoint orbit, and those are Hamiltonian. So we can add these two Hamiltonian moment maps together with a minus again because of this inverse of the symplectic form. And well. Okay, maybe I shouldn't, but this I mean this is the inclusion of O psi into G star. Because if you remember that for coadjoint orbits, this is how we got the moment map. It was simply the inclusion into G star. And this is a Hamiltonian. This is Hamiltonian G space. Let's do to check. It's simply a product of two Hamiltonian G spaces. And okay, so let's look at what the preimage of this new moment map, this new prime, what is the preimage of 0? Okay, so what is the preimage of 0? Well, when is this thing 0? It's if the first sum equals the other one. So this is simply the collection of all points m and maybe eta inside here, such that the value of the moment map on m is eta. That's what it is. And where does this live? This is a subspace of m times all psi. Okay, but what I can do here, here I have a natural surjective map to m, the projection. And so what happens? What do I get if I apply this? What is the thing? If I project to m, what do I get? Down there. What are all I take? What are all possible m's? What are all possible m's that I get inside here? Anyone has any idea?
All m's, no? Because it's all m's for which there exists eta.
Yes, but eta is restricted in the range.
Okay. So it's interesting.
Yeah, eta needs to be in here. So this is in fact this is the preimage of the entire orbit of the coadjoint orbit, which sits inside here. Right. So I get or if you want, this is a. You can say that this is a union over all etas in here of pre-images of eta. And not just this, but you also easily see that this map is an isomorphism. Because each of these things, well, yeah, it's the. Should I draw a picture? So I have M, I have G star, and I have an orbit. I don't know how to draw an orbit. Let's say this is an orbit. It's all psi, with the point psi. So at each point eta here, I get a pre-image here. So probably we can imagine some sort of picture like this, where you can have some family of pre-images. Each of them will be pre-image of a different point. And yeah, well.
You want to explain why it's an isomorphism?
Yes.
So if you know M, you know eta, because eta has to be the
Yeah.
image of
Thank you. That's
M by
yeah.
mu.
Yeah, right. Yeah. So these are in fact determined. If you know M, then you know what mu is. So yeah. So actually, the progression to M determines the whole thing. Yeah. Thank you. So okay, and furthermore, is okay. Final thing. This is actually a G equivariant isomorphism. So the action of G up there, which rotates both things. Well, this is okay because the action because this projection was G equivariant. So both of them. This one, but yeah. This is a G equivariant projection. Yeah, the reason is simple. Okay, so now we can apply the previous proposition. Maybe let's ignore regularity and such things for now. So we know that this thing is symplectic because it simply fits into the quasi-atomic reduction framework. So now what is the preimage of 0? Well, as we just showed, this is isomorphic to this one. And it's G equivariant, so the G quotient is the same, and this is precisely what the thing was. So this is symplectic. By the way, notation with the double quotient, it's supposed to signify that one reason for it is that like the dimensionality of the quotient is actually dimension of M minus, and you remove 2 times the degrees of freedom of G. Because first you restrict to the yeah, okay. Yeah, it's a preimage of a point in G star, which means that it's a G dimension of G work of conditions, and then you reduce it move quotient down. So then there is also some higher versions of this where you like quadruple, 1, 2, 3, double, triple, quadruple. Okay. Okay, review time. Okay, good. So then there is one last thing that no, sorry, there is 2 more things that one can say about this in this general context. So you can wonder what is the algebraic characterization of this Hamiltonian reductions. So let's say that so let M be a G Hamiltonian G space, I think. Now we can define 2 interesting ideals. Maybe this is not the ideal way to do it, but so let me define an ideal. Okay, and let's take psi in G star. So, well, I define this to be the vanishing ideal for the preimage of psi. Okay, so this notation means that if I say that if I have a submanifold S, then by this is space of functions which vanish such that F restricted to M is S is 0. Okay, I will just denote it by capital I with subscript denoting the submanifold. Okay, so let's take this one to be this. Now, well, we can show that we can actually relate this to the vanishing ideal of psi. So if you would have the vanishing ideal of psi, which is something that lives in G star, it's an ideal inside functions on G star. You can probably actually write set notation, and you take the fallback of that, and then you take the generator of that. This should be some general fact. Ideal of the pre-image is generated by the fallback of the ideal. Could be checked in coordinates if one wished. Okay, and second fact. Second thing, we can take. Remember that we have this group, the stabilizer. So that group has a subalgebra. G psi. This is the Lie of G. So this is the Lie algebra of this.
We're discussing the.
Whether I think so, because it's bigger. Oh, I think okay. So anyway, so remember that we had this Lie algebra of the stabilizer, and this is all sitting inside G. But G is a very special kind of function of G star. If you give me an element in G, that produces a function on G star by pairing with G. So those are a special subclass of linear functions in here. So okay, so this is a subset of functions. So now I can pull them back again and take the ideal generated by that. And I have two ideals. So I have I and J. They are both ideals inside C infinity of M. And now the proposition is that if you go to this reduced space and you look at the algebra of functions there, then algebraically you can characterize this as all functions C infinity M, such that if you commute them with J, you end up with I, and then modulo I. So it has sort of similar, it's very similar to the Poisson normalizer data before. Okay, so let's try to absorb that before I erase. Any questions? Also from the online audience.
Hilarious.
Hilarious. Okay. Okay, so the proof of this is very short. Yes, all such proofs go. So what is the algebra on the quotient? What is the quotient? First of all, it's the pre-image point modulo stabilizer. Okay, so what does it mean that I take functions on the quotient? I take functions on the big space, and then I take those that are invariant of the orbits. Fortunately, now we have a group that acts, so I can say that those are the ones that are invariant of the group action, which people usually denote by putting the thing here. And I can replace the group by the algebra because I have some connectedness of the group. So I could normally I would actually this means like G, Xi, invariant functions. Normally I should put big G for the group, but since it's connected, it doesn't matter. Okay, so now what does this mean again? What is the this was a subspace of our M. So functions on there could be identified with functions on the big manifold model of the vanishing ideal of that thing. Functions on a submanifold is the same as functions on the big thing model of the vanishing ideal. Okay, and then, well, okay. Now what I would like to do, I would like to apply this exponent to this fraction. Well, not really, but okay. So I want to write this thing in terms. I want to put G-invariant functions here on the top, but then you know, like, okay, I will write it. So this is really functions on the top, which I want to be G-invariant up to functions that vanish on here. So what I really want is that those are functions such that if I take this Lie algebra and I act on my function, such that for all x in Vxi, xm on f will vanish on the submanifold. Okay, so invariant functions like this, if I want to talk about invariant functions here, I don't really want. Okay, maybe this requires a little bit of thinking, but so I want invariant functions, but I only care about them on the submanifold. So essentially what I want is that I take all the functions that I have, and I want that they are invariant on the manifold, on the submanifold, which should be this condition. And if I differentiate them, I still line with ideal, and then I model by ideal. Anyway, okay, we can think about it more, but I think I don't have that much. That's a typical excuse, but anyway, we're running near the end of the course, so I would like to get to some other parts. But okay, so what is it that I want to write now finally? I want to say that this thing is the same as well, what is this? This is the Hamiltonian vector field of this is the Hamiltonian vector field acting on function f. So this is the same as Poisson bracket with f of the Hamiltonian that generates this. And what is the Hamiltonian that generates it? That's precisely encoded by the moment map. That's how the moment map was defined. And okay, one fun fact: this thing is the same as the pullback of this. That's a fun fact. That's actually the pullback of this. Sorry, for all things in here, which in particular are functions on G star. So if I regard x as a function on G star and I pull it back along my moment map, I get a function on M, and what is the function is the same as this one. And you can easily see that by evaluating both sides. So okay. If I pull, for instance, if I pull back this function and I look at a point M, in M, what is this? This is pulling back a function and evaluating it. This should be the same as x evaluated on mu of M, which is the same as pairing of x and mu at M, which is the same as mu x evaluated at M. So why am I writing that? Because now I maybe there's a plus minus. Okay, so then this should be precisely what we have here. So I want to take the Poisson bracket. You see, I already got it to the same form where I modeled by I. And the thing about it says that if I model the Poisson bracket of my f, together with anything that I pulled back from the linear functions that presented my j. Sorry, this was so this should be the same. Yeah. So this should be precisely my J. Let's say. Yeah. This is precisely Poisson bracket F with something in J should be in I. Okay. And the thing I'm not showing. The thing I will not show you is that. So this shows that as far as the space goes, then you can identify the space that like the algebras of functions are coinciding, but you also need to show. The other thing to show would be that actually the symplectic form that you get on this, which comes from the previous proof, is the one that you inherit from here, but that I will do. So I will declare this the end. And then okay, any questions?
So it seems that there are two kind of equivalent ways to describe this space, like the preimage of the point psi model, or its preimage of the orbit.
Yes. You want to say why they are the same?
No, I don't think, but okay. Just in general, preimage of the point it doesn't have. I think it doesn't have a nice, like, symplectic geometry interpretation. It's not quite okay.
Right.
So one should, yeah.
Yes.
Okay. From those two viewpoints, I would say that the preimage of the orbit modeled by whole group is
Better.
better.
Yes.
So
Okay.
that I was a bit surprised that, but yeah, I guess the proposition is true. There we use the other description in this.
Right.
But
Okay.
there's no contradiction.
Right. Good. Thanks. Okay. I hope that was audible. So, yeah. So Jan is saying that the.
But the important point is that the preimage of the point is not quasi-approximate.
Yeah, preimage of a general psi is not quite approximate.
As one can see on the inclusion of the quadrant orbit into the algebra. Because preimage of the point is just.
Yes, the point.
Yeah, there is no regular idea.
Yeah. Yeah, thank you. On the other hand, the preimage of the simplex of the whole quadrant orbit.
It's quite.
It's the question of which is quite approximate.
Yeah, for example, there, like, for quadratic orbits, one can do this Hamiltonian reduction, you just get points.
Mm-hmm.
Even though the moment map is it's not the regular value of the moment map.
Yeah. Yeah. Good. Any further comments? Questions? Complaints? So, there is one more thing I wanted to say before switching back to Courant algebroids. And that's to say that we know that we have now used the Lie group version of the story. There was a group in the ring. So let me now make a remark on what happens when I replace the group by an algebra. And let me call this is an established notation, or maybe not, but it doesn't matter. A Hamiltonian small g space for the algebra. So this is a symplectic manifold. M omega together with an action of the algebra on M. What does that mean? What does it mean an algebra act, the algebra acts on M? There's a homomorphism from G into vector fields. And we want to have a moment map. And now two conditions. Now we want that mu is G equivariant. And the second condition is the same. So for all x in the real algebra, this fundamental vector field, which is simply the image in here, should be Hamiltonian, and the Hamiltonian, all the Hamiltonians are collected in this moment map. So the only changes with respect to the previous definition was that I use G here, and here, and here. Now, well, one reason why I don't see perhaps this thing as often is that this thing actually has a simple description. Well, I think it's a different description. So, Hamiltonian small G space is the same as a Poisson map from M to G star. Well, namely the moment map. Okay, is the statement sort of clear? So let's if not, then let's clarify further in the proof. So first observation is that these fundamental vector fields, these are in fact determined by mu and the second condition here, mu and this condition. Okay, that's what the second condition says, that the fundamental vector fields, which in our case this is the entire data of the action, they are actually Hamiltonian, where the Hamiltonians are all collected in this one map mu. And so in fact I can I can simplify the above definition, and I can in fact forget about the action. I can remember just the map here, and I can forget about the second condition, because the second condition only says that these vector fields are defined using this. But I can't really forget about everything, because I want to say that something is G equivariant, so I need to know what the action is. So let me just phrase it like this at the moment. So first statement is just to see that the data that I have here are purely determined in terms of mu. Okay, the question now is how to translate this first condition in terms of the equivariance. Okay, so let's so mu is G equivariant. What does this mean? So far, let me just try to rewrite this condition. So what does it mean that mu is G equivariant? It means that on the level of functions, if I would like to, so it means that well, how should I say it? So okay, let's say let me take this for all things in here, and for all functions on the Lie algebra. If I pull back a function and then I act with this xm, this should be the same as acting here on G star and then pulling back. Okay, so those two things are the vector fields. But in fact, functions on G star are all kind of generated by linear functions there. So in a suitable sense. So I can just as well say that I have two things in here, x and y, which are in G. And I want this. Okay, I can just reduce it to linear functions because they generate all functions taking some appropriate completions. And the only thing to do now is just to rewrite what these two conditions are, and you will see that they precisely correspond to the fact that it's the Poisson map. So, okay. For instance, what is this thing in here? What is this? What is the action of this fundamental vector field on G star. How does this thing act on a linear function? What is this? Is that question clear? I mean, there are many symbols that are playing various roles. Okay, so this thing, remember, this is an element of G, which is in particular a linear function on G star. And this thing is a vector field on G star, given by the quadrant action. So what is this? I get a function again, I get a function on G star. So let me evaluate that function at a point xi in G star. Well, okay. So what is a fundamental vector field? It's the derivative at equals 0 of the coadjoint action, and then we use the minus sign of t times x acting on y, evaluated at psi. How does the coadjoint action works? It's the transpose of the original of the adjoint action. So this is the of y acted upon the no, sorry, what did I mix up? Oh no, God, okay, sorry. Moving too fast, I didn't notice that. Sorry, is this expression clear at least? Yes. I'm checking what the the fundamental is. I'm now on G star on the Poisson manifold G star, and I didn't emphasize that, but it kind of Poisson map means that both of these things are Poisson. This one is Poisson because it's symplectic, and this one is Poisson because we saw that last semester. This is a basic example of a Poisson manifold. The wall of the algebra. And its symplectic leaves are the quadrant orbits. Sorry, if it's too fast, then you can pause the video. Okay, so I'm looking. Okay, so I'm differentiating a function at a point. So what does that mean? It means that I look at the integral curve of this thing. I evaluate my function at a curve starting at here, which is given by this, which is precisely at star e to the minus dx of psi. And now I use the fact that the quadrant action is defined using the transpose. So this is really the adjoint of e to the tx of y of y, and this thing is paired with psi.
So could you maybe just write down just the description for the fundamental vector field for x on this manifold?
It's this. This is the or the derivative of this is.
Okay. I see.
Yeah.
So that's the value of x. Okay.
So in general, this thing would be this thing at a point m is d of dt t equals 0 of e to the minus dx acting on point m. And in our case, the action is the coadjoint action. So in our case, m was c star. That's our manifold. And we took a point psi, and this thing is simply d over dt equals this, and then this is the coadjoint action acting on psi.
Okay.
And now, if I take a derivative with respect to this vector field, it means that of a function, it means that I can take the function and I evaluate it on this curve, and then I take a derivative. Good. Okay, I know what the differential of adjoint action is. It's simply the commutator. So this is the commutator of x and y evaluated at psi.
Yeah. So that was the general action, how you defined it, including this minus sign that you said at the beginning of today. But now you are acting on functions, and shouldn't, if you have group action on function, act with the inverse inside the diagram to make it both left action?
No, I think it should all play really fine. Like if you have a general curve and you have a derivative, So you have a vector at 0 or
Yeah.
somewhere, and you act on a function, and this is f of gamma of t, so you don't put minus t there. It just uses that formula.
But wouldn't this change the left action to right action if you do it? Because of the, because it's kind of contrariant argument of the function where you're acting. Just like you don't even need to differentiate. Just the question is about the action of g on functions. If you know how they act on the domain of those functions, I would say that the g acting on f is
Yeah, but they
G
should
inverse.
be contrariant because we are pulling back functions, and there you expect them to be an anti-homomorphism.
That's why you take the inverse of the action
Okay.
to get a left action on functions.
Yes.
So
So that's you saying it's already included there.
Something like that.
if you want to get like the derivative of the action, you act by g inverse
I mean here.
or e to minus px.
Yeah. Yeah.
Yeah. So this is general for any action of big G on n. You would act with exponential of minus tx and differentiate it with respect to t to get the left action on f actions.
Yeah.
Yes.
And so now it should input formula.
But now it looks like the y is a function,
Mm-hmm.
and so if I want to act on the function, I should act the inverse on the argument of the function.
I see what you're saying, but I think in that case that I think in that case I'm just using this, and that there is no
Okay.
minus sign appearing there.
So there is another minus sign because the action on the dual has a minus sign.
Yeah, there is another minus.
Yeah, but that's fine.
I think there is no sign in the transition that you are saying. Yeah. Okay, good. So now what is this? This is simply taking x, y, regarding this as this is a function on G star, and evaluating the psi. So I can conclude from this that x G star, the fundamental vector field, when it acts on any y, it is bracket of x and y.
Which is left action, so we know we got it correct.
Sorry?
This is left action.
Yes.
So
yes.
we
Either
we
we
got
we
it
made
correct.
an even number of side mistakes, if any.
Yeah.
Okay, so now just going back, what does it say? It says that, going back to that, here, what do I have here? At the end, just collecting pieces, so let me rewrite it. Okay, so this, I just rewrote that thing. So now the right hand side, we know that this is simply mu star of the commutator.
So I'm kind of confused about that. So why is the result of the action of the fundamental vector field actually an element of the Lie algebra? Or
It's that was the result of the class. So this thing in general you want this is a number, right?
Okay.
This whole thing is a number, and the number came out to be this one.
okay.
And I wrote the number in a way that it's a function evaluated at psi. And so now both the beginning and the end are written in a way that they are functions on G star evaluated at the point. So I conclude that the two functions are the same. So here both sides here I regard them as
Okay.
functions on G star.
Makes sense.
They just happen to be linear functions. Fortunately. Yeah, this is a complicated thing. So yeah, you can pause the video and try to figure this out before continuing. Okay, so what do we have there? Yeah, right. So what is the left hand side here? I have a function on my manifold M, and I'm differentiating it in the direction of this Hamiltonian vector field. So it's the same as Poisson bracket with the corresponding Hamiltonian. What is the corresponding Hamiltonian for this? It's precisely mu paired with x, which, if you want, is the same as mu pullback of x and mu pullback of y, and mu pullback of y in Poisson bracket, and we are saying that this is the same as this. which incidentally maybe I should have. Oh yeah, was I stupid? I could have skipped this calculation about, because the thing I really need is just that this thing is the same as the Poisson bracket of x and y. This is the definition of. Well, anyway, it was good to revise this once, but I actually wanted just this, which follows there kind of. But okay. Yeah, that's the definition of Poisson structure of G star. Yeah, sorry. So this was just a nice revision of how it comes to that. But anyway, so the thing you see at the end is this is the definition of mapping Poisson. The pullback of Poisson bracket of pullback is the same as pullback of the Poisson bracket. And again, this was checked on linear functions, but linear functions induce all functions. So yeah, that's the answer. Sorry, that was a bit fast, and also it an unnecessary step apparently. Or rather a revision. Okay. So given the time, I suggest maybe to do the following thing. Forgotten it now. Any questions? Oh, if not, then I will. Okay. So there is. So now the last part awaits us. Because this thing, as you can see, so far this was a little bit unconnected with the rest of the story. But the reason I was going into this is, first of all, it's a nice thing and it maybe is useful to see it. So I try to show it to you from various sides. But also, there is an analogous construction on the level of Courant algebroids, which is called Courant algebroid reduction, or reduction of Courant algebroid. That one is typically studied on the level of Courant algebroids, so meaning in the language of vector bundles. While it turns out, in fact, that kind of the arguably the conceptual explanation of that effect of that thing actually comes from the realm of this graded geometry. In which case we know that Courant algebroids are simply symplectic manifolds in this graded language. And so it turns out that actually this reduction of Courant algebroids that I will sketch now, that's where I'll finish, that actually does have it's sort of the best explanation of it is in terms of this graded symplectic geometry and Hamiltonian reductions. Okay, so let me do the first part of that today. So next time I will finish this and then I will hopefully sketch some connection to the Poisson methodology. So equivariant. For now, equivariant reductions. Oh, sorry, let me just call them reductions. Reductions of Courant algebroids. Okay, so I assume that you all have to remember what Courant algebra is. It wasn't that long ago. It's a vector bundle with some structure. E over m, and there is a bracket, pairing, and there is an anchor from satisfying some bunch of axioms. Okay, so there is a way how to reduce Courant algebroids, which is similar to what we've seen before, but so far it will not be clear how. So that's for later. So for now, let me just set up the stage. So let now G be a Lie algebra with an invariant pairing, but I will now not require this to be non-degenerate. So with a potentially degenerate invariant pairing. I will call it like this. And in fact, if you like notation, then I could just as well say that this is an element of the second symmetric power of G star, which is invariant under G. This is what it means to be invariant. I wrote it in words and then in formula. So now, having such an input, we say that the Courant algebroid is G equivariant. So G equivariant Courant algebroid This, in a sense, would be an analog of a Hamiltonian T-space. This is a Courant algebroid over M together with a map chi that goes from G into sections. And I will require it to preserving both the bracket and the pairing. And also I will impose one technical condition, and such that this is a bit negotiable, but I decided to include it, such that chi is injected at every point. Okay, because applying chi to an element of the Lie algebra, I get a section, and I want that. So at each point on M, I get a mapping to the corresponding fibers. I get a section, but restricting to a point, I get a sub-fiber, and I just want that this thing is injected there. Okay, is it clear? It's kind of like a homomorphism, which is what it is. Now, notes. So what does such a thing give us? So we have this map chi, and there are various things that we could do with a section of a Courant algebra. You can use the anchor to map it to a vector field on M. But if you remember, this was also something that we discussed the other term. Then there is a way to produce a vector field on the total space, which actually covers this vector field M on M. Okay, this is from last semester. So see last semester. This was the way how sections of Courant. This was kind of what the bracket was, or what the you can say this is okay, or the generalized derivative or something. So this just says that for every section of the Courant algebra gives rise to an infinitesimal automorphism of the Courant algebra. And one way to understand that was that it was a vector field on the total space of that vector bundle. Well, in other way, in this way we have vector for every element here we get a vector field here, and so this thing gives an action of G on E on the manifold E. And also on M. Okay? Because as we said before, an action of Lie algebra is a homomorphism onto the vector field. Okay? So although it was formulated like this, it was a section, it was a homomorphism into the sections. In fact, it really gives you an action of the Lie algebra on the whole structure. Okay. And now definition, go from algebras to groups. So if this action integrates to an action of a connected group, this is just again some sort of technicality, the group G, we say E, the Courant algebra E is in fact capital G equivalent. But the important part of the statement was in the first definition. This is just to say that I want it to be actually corresponding to some group. Okay. So far, so good?
Can you remind me? So you need bracket and also the pairing on star.
On what?
Sorry, you want this map chi preserve.
Yes, preserve. Yes, this just means that chi of x chi of y, if I take this bracket, it should be in G, sorry, in E, this should be chi of the first one we also bracket. So there's no two other or pull back.
So that's the usual, okay, so the usual algebra bracket, and then the other one you specify as input. Yeah, okay.
Yeah, this thing should be on this one. This should be this should actually be the
This is the one, the assumptions.
yeah. This is the one in here.
Yeah, so this is the effort. So first one is just the usual bracket, and the algebra bracket. Then the second one is the one that you are just assuming.
This one.
Yeah.
Yes, that's right. Yeah, and in fact, I should. Yeah. In fact, the only meaning. Yeah. So what I mean here is this is a constant, so I really want this to be that constant. So yeah, this. Yeah. So, yeah. So this is the condition of error. I should probably maybe can write like chi full level constant. No, I shouldn't.
And there is no anchor like the
There's no anchor. No. No.
It's like 0.
Yeah. Well. No. Well, in a sense, well, this. But so you're trying to see what this would be more general if I would have like a map from a Courant algebra into it.
No, not exactly what.
Yeah. No. This actually comes from more general setup like that, but yeah. But this is only one that will. Thank you. Yeah, have a good hour.
No, it's just like I'm just now reading it. So.
Okay. Good. Okay, so that's last thing before setting the theorem. So now suppose that we have such a G equivalent algebroid. Now where is it? So we define a interesting bundle, a vector bundle. We define the vector bundle. I will call it, I don't know, E tilde. Over M. And I will define it by requiring that I take this thing, the fiber of this thing, I will take it to be the, so I take, by this is a notational character, like this M is a point of M. Okay? So I just look at the image of this thing, which gives me a bunch of sections, and then I look at what those sections give me at the point M. Okay, so this is really an element of the fiber at M. And now what I do is I take the complement of that, and I divide it by something, and that something is similar to the image of kernel of G. Okay, so kernel of G, this is all elements in X, so this is all elements in X such that, well, they are orthogonal to everything. Because as I said, the pairing could be degenerate. If the pairing is not degenerate, then this kernel is trivial. If the pairing is 0, then kernel is everything. But if it's something in between, then I have to use this unfortunate thing. Now, the assumptions on the injectivity in the fibers ensures that this thing actually has a constant rank. So this is actually a bundle. Whatever. Technical. Okay, now the theorem, which we are not going to prove, but I will try to sketch next time how this thing can be seen in terms of Hamiltonian connections. So, theorem says that if we start with a G equivariant Courant algebroid, if this is a G equivariant Courant algebroid, and again, technicality with the action of G of E being free and proper. Okay, feel free to ignore the technicalities. Then we can form a new Courant algebroid. We call it E red, reduced. And this thing, again something I didn't say, never mind, is this tilde thing multiplied by G. and this is a vector bundle over the quotient. So the claim is this thing inherits a chronological structure. So yes, there is one underlying statement that I didn't say before, but the fact is that this E. Okay. So how easy is to see that? So so the underlying claim here is that this quotient bundle that I have here, this thing still carries a G action. So in fact. There is a G action, but anyway, since I'm not proving it, I will allow myself to go to debate. So it's the point that you make a smaller bundle, like you really take this kind of sub-quotient, like the sub-bundle quotient and out by something, you get a different sub-bundle. It's still a sub-bundle over M, which carries an inherited action of G. And now I quotient it by that action, and it becomes a new vector bundle over the quotient. And the claim is that there is a natural way this inherits the Courant algebroid structure. And last statement maybe that, okay, just for those of you who encounter this in practical life, if the original algebra was exact and the pairing of the Lie algebra is 0, then the radius one is also exact. It's also useful statement for those of you who use Courant algebroids on a daily basis. Okay.
So what is it's like always heroic, or heroic?
Transitive?
Yeah.
Well, if the original one was, then this one is. Well, what I remember for sure is that this was exact, and this is arbitrary, then the result is transitive.
Yeah.
You start non-exact, then it's transitive. Surprisingly, I'm not sure if you start with. No, you can take the group to be the identity group, like the trivial group, and then the Courant algebroid is the same as the one that was originally there. So if it was not transitive, then it won't be transitive.
Yeah, I mean, if you saw it an exact one.
Yeah, then it should be in general transitive.
Yeah.
Okay, so okay, I think this is a good place to stop. So next time, so the takeaway message is that there is a procedure on the level of Courant algebroids, but as you see, it involves some steps. It's not super immediately transparent, and you're making these quotients and everything. So in fact, I mean, also I won't be proving it, but instead you will see how things get more transparent when you do the differential gradient language. So next time we will recall a couple of minutes how Courant algebroids can be seen as the sigma 2 manifolds, like symplectic gradient manifolds, and then we will see how this condition, how equivalence actually translates to a moment map condition on Courant algebroids. So yeah, thank you.